Hi everyone, welcome to lesson 45 in our trigonometry unit. Today we're going to talk about resolving vectors into its components, which means taking a vector and splitting it into a horizontal and vertical component. So let's get started. In physics and engineering, we often deal with vectors like forces or velocity that act at an angle. To make calculations easier, we break down these diagonal vectors into perpendicular parts. In the horizontal, the x component, and the vertical, y component. And this process is called resolution. So the concept is, imagine a vector acting at an angle of theta, or right here, relative to the positive x-axis. We can treat this vector as the hypotenuse of a right-angled triangle. So the x component, ax, it's a little small, so I'll write it bigger, ax, is how much the vector moves from left or right. And then the other component in the vertical direction is ay, and that describes how much the vector moves up or down. So formulas using basic trigonometry, like SOHCAHTOA, the trig ratios, we can derive the following equations to find the magnitudes of the components. So to find the horizontal component of vector A, we would take A, the magnitude of the vector, and multiply it by the cosine of the angle, theta. To find the vertical component, we would take the magnitude of the vector A and multiply it by sine of the angle theta. So just a note, these formulas are based on the assumption that theta is measured from the horizontal axis. And if the angle is given from the vertical axis, and then these will actually be switched around. So why do we do this in the first place? Resolving vectors is essential because it can help us take a look at motion, particularly in projectile motion, which again connects back to our quadratic unit, but we can analyze the motion of objects horizontally and vertically, and they don't really have to affect each other. The other thing is a vector addition, and it's much easier to add multiple vectors by summing their x components separately and then summing their y components separately than by using complex geometry. So another way to make things easier when we're working with multiple vectors to add. So let's take a look at some examples. So we have a word problem to start off. A soccer ball is kicked with a velocity of 30 meters per second and an angle of 55 degrees to the ground. Calculate the horizontal and vertical components. So let's go in here, zoom in a little bit, and let's work on a little bit of a drawing. So here, I would start with my little soccer ball, and I would draw in a vector. This represents vector A, and it is given to be, the magnitude of vector A is given to be 30 meters per second. So I'm going to write that here, 30 meters per second. And it is at an angle, I'm going to try this dotted line first to represent the ground, and it acts at an angle of 55 degrees from the ground. So here along the ground would be the x component of A, and then here vertically would be the y component of A. So we see that the x and the y components help us form a 90-degree triangle. And so we can go back and use our trig ratios, and that is how we derived the formulas. So from the other page, the x component is equal to the magnitude of the vector times the cosine of the angle. In this case, we have 30 meters per second times the cosine of 55 degrees. You use your calculator, make sure it's in degree mode, and what we get is 17.2 meters per second, and we have to have a direction. This is the horizontal component, so we're going to put to the right. Now the vertical component, AY, is equal to the magnitude of the vector times the sine of the angle. So here we have the magnitude of the vector, which is 30, and we're going to multiply it by the sine of 55. Again, using your calculator, you'll get 24.6 meters per second, and that will be in the upward direction. All right. Let's take a look at our other word problem. So a crate is being pulled up by a rope with a force of 120 newtons. The rope makes an angle of 25 degrees with the vertical. Find the horizontal force pulling on the crate forward. So it already says be careful. Since the angle is with the vertical and not the horizontal, the components are going to be switched. So let's draw a diagram. So I have a crate and it's being pulled by a rope with a force of 120 newtons. And this force makes an angle of 25 degrees from the vertical. So the angle in here is 25 degrees. Now, if I want to find the horizontal pulling force, that is going to be right here. And I'm going to call it AX for horizontal. Now, if you look at our right angle triangle, theta here is 25. I want to know the horizontal. And so from the angle, that is opposite over the hypotenuse. Opposite over hypotenuse with our trig ratios is really SOHCAHTOA. This is really sine. So this is A times the sine of the angle theta. The magnitude of the force is 120 newtons. Sine and their angle that was given was 25. Using your calculator, again, make sure it's in degree mode. You'll get an answer of 50.7. That'll be newtons because it's a force, and that will act to the right. Good, let's take a look at a different example. So in this case, we have an airplane flying at 200 kilometers per hour at a bearing of 120 degrees, which is 30 degrees south of east. So resolve this into east and south components. Again, let's start with the diagram. Here, the airplane is flying 200 kilometers per hour, which is 30 degrees south of east. So south is down, east is to the right. And so I'm going to draw my vector off in this direction. So if this is my vector, then it has a magnitude of 200 kilometers per hour. And this vector makes an angle of 30 degrees south of east. So my horizontal component here is X, and this is a Y. Actually, let's call them east and south. So this is going to be A east, and this will be A south. Okay. The east component here in this case is actually our horizontal component. So A in the easterly direction is going to be A cosine theta, which is 200 cosine of 30. Using my calculator, I have 173.2 kilometers per hour east. The south component, which is the vertical component, is going to be A times the sine of the angle, in which case it's going to be 200 times the sine of 30 degrees. And with a calculator, I get 100 kilometers per hour, and the direction is south. So most of those examples showing us how to resolve a vector into its horizontal and vertical components. Let's take a look at an example where we would have to find the magnitude of the vector. So if I take a look at this diagram, you have vector A, but the magnitude is not labeled. But it's a little fuzzy, but if I take a look at the horizontal, let's call this AX, and we count the units, it's 1, 2, 3, 4, 5, 6 units. 6 units. And then in the Y direction, again, 1, 2, 3, 4, 5, and 6, it's also 6 units. Well, again, we have a right angle triangle. And how are all the sides of a right angle triangle related to each other? Well, they are related by Pythagoras. So writing out the Pythagorean formula with these variables, I would get something like a squared is equal to ax squared plus ay squared. Subbing in, I will have 6 units squared plus 6 units squared. That will give me 36 plus 36. And then a is going to be equal to the square root of 72. And so the magnitude of my vector A comes out to 8.5 units. Great, but what if we want to know the direction? So let's take a look at finding the direction. So I'll take out my triangle from the top here so we can draw it out a little bigger and label all the components that we have. And we know the magnitudes of A, that's 8.5. And we know the magnitude of AX, the horizontal component, is 6. And the magnitude of the vertical component is also 6 units. In order to find the direction, I'll have to be able to figure out what this angle theta is. Since we have all 3 sides, we can use any of the trig ratios. SOHCAHTOA. And so for this example, I'm just going to use sine. So the sine of the angle is equal to the opposite side over the hypotenuse. In this case, 6 over 8.5. In order to solve for theta, I have to take the inverse sine. of both sides. And again, using your calculator and the inverse sine function, I get an angle of 45 degrees, which hopefully you can see makes sense because we really have an isosceles triangle. Both legs of this triangle are equal to each other, and so theta should be 45. We're talking about a 44, 45, 45, 90 special triangle. So if we put it all together, my vector A is equal to 8.5 units in a direction that is right 45 degrees up. We're going to move on to a couple more things. Here we have another example. I'm going to think back to our coordinate grid and the quadrants of the grid. So here I have just a schematic. Find the vector represented by the terminal arm on a coordinate grid. Draw the terminal arm before you solve the missing component. So if I want to find the horizontal component of a force of 40 newtons at 95 degrees, what I have to do is to determine in which quadrant, 1, 2, 3, or 4, does this angle lie in? Well, we know that the first quadrant goes from 0 to 90, the second one goes from 90 to 180, 180 to 240, and 240 to 360 in the fourth. So 95 degrees will fall somewhere in this third quadrant. So my full angle here, from here to here, is 195 degrees. What this does is helps us find our reference angle. Let me change colors. Our reference angle is the angle from the x-axis. So here I can start to draw my x and y components. So my y vertical component of my force and my horizontal component of my force, and this angle in here, the reference angle, with a little bit of subtraction, is 15 degrees. So let's go over. I want to find the vector's horizontal component. There. All right. So the vector's horizontal component is AX, and the angle is 15, and so it's adjacent to the angle. So that is going to be the magnitude of the force times the cosine of the angle. In this case, the magnitude of my force is 40 newtons. Cosine, the reference angle, 15 degrees. And again, with my calculator, it'll come out to 38.6 newtons, and it is going to be to the left. So there you go, how to put a vector onto a set of coordinate axes and find reference angles by drawing terminal arms. And the final thing that we will take a look at is a word problem. And of course, just like we've been doing with all of these components, drawings really help. So Joe pulls Sally on a skateboard with a force of 15 newtons to the left at an angle of 34 degrees to the horizontal. Find the x and the y components. So in this case, because it's to the left, this little box is going to represent Sally, and Joe's force pulls to the left at an angle of 34 degrees to the horizontal. and the force is 15 newtons. We want to find out the x and the y components, ax and ay. To find ax, we are going to use cosine again, magnitude of the vector times the cosine of the angle, which case is 15, times the cosine of 34 degrees. With our calculator, we get 12.4. That direction from our picture is to the left. And then to find the vertical component, it's going to be the magnitude of the vector times the sine of the angle. So it would be 15 sine of 34 degrees. And my vertical component comes out to 8.4 newtons, and that will be up. So there you go. We're done with this lesson 45. You can work on the worksheet 45 in Google Classroom. And if you need any support for this, just reach out. All right, bye-bye.